Hello everyone, I am Swarda Kulkarni and my partner is Amin Shafi. Today we are presenting our project on variation-aware placement and inter-device matching of ring resonators for silicon photonic interconnects under the supervision of Professor Nikdas Mahadi. As we know that silicon photonic devices are very sensitive to any kinds of variation and it makes difference in the output, it is very necessary to try and include the variations while designing any device. Of all the components used in silicon photonic devices, we have selected micro-ring resonators for testing the sensitivity in silicon photonic interconnects, since it is larger in size and is highly sensitive to wavelength. These devices can also act as filters of the optical signals. Some of the important parameters in MRRs are its radius, width of the waveguides used in rings as well as the input-output waveguides, gap between the rings and the waveguides, and the coupling coefficient. For our project, we have used some important relationships from the previously related work. The MRRs being sensitive, slight difference in parameters will change the resonance wavelength. The resonance wavelength is dependent on the geometry, that is, the width and thickness of the waveguides, and the ring which is used to calculate the effective index of the waveguides. The motivation behind considering our project was due to the evident issues in the MRRs. The MRRs are susceptible to variations. We are considering the process variations here. So what are exactly process variations? These variations are also called as fabrication variations as they are originated from the physical properties of the process the foundry uses while fabricating the devices for us. So whenever we plan to design a component, in our case MRRs, which have specific geometry and resonance wavelength, it works perfectly while simulating. But the actual fabricated device might not be as perfectly designed similar to the simulated design. And that is because of the variations during the fabrication process in terms of thickness, width, or radius of the component geometry. This may look like a trivial issue when we are considering only one or two MRRs, but in a single device, there are multiple MRRs used. And these variations will accumulate for each of the MRR and have drastic effect on the output of the device. For our experimentation, we are considering two different variations and how they affect the inter-device matching and the placements of the MRRs. First, we changed the distance between the pairs of MRRs that are matched for calculating the variations. And second, we changed the channel spacing while placing the MRRs and saw how it affected the execution time. Now, my partner Amin will discuss the methodology used and the result obtained from the experimentation.
So, what are the objectives of this project? First of all, we have to understand the fabrication process variations and how to plot them in MATLAB. Then we should understand how to exploit the fabrication process variation maps or FPV maps to obtain the variation-aware design and placement of silicon photonic interconnects and understand how they will contribute to our design procedure. Then we have to simulate a network of MRRs comprises of rings, which we have to take them pair by pair and match them together to calculate the resonance wavelength shift and channel spacing shift and expand the algorithm and the method that we used for network level design with more MRRs. At the end, we have to develop algorithms to match the MRRs according to resonance wavelength and the optimal channel spacing that we could have under the variations that we have by definition. And then we develop algorithms to optimize the device design and geometry according to the FPVs for the selected die on the wafer based on the result on the previous steps to minimize the wavelength shift and change in the channel spacing due to fabrication variations. First of all, for a given wafer with a size of 200 millimeter times 200 millimeter, we randomly select a die with a size of 22 millimeter times 22 millimeter to place our ring. Let's say that This is the randomly selected die on the wafer. Then for the chosen die, we select a variation related to the width, which its color map has been showed here, and the radius and the thickness that we have here, which were initially provided as .csv Excel file, which was 100 by 100 matrix of the variance of the variations related to the radius, thickness, and width, and the distribution of them, which their color maps can be seen here. So till now, we have a selected die on the wafer. Then we start from a 400 nanometer width of the ring and input and output waveguide and the gap of 100 nanometers since it has a maximum coupling. Then we perform a meshing through the selected die according to the FPV maps we have with a mesh size of 10 nanometer. For each point of the grid mesh point on the selected die, we estimate the variations related to the thickness, width, and the radius through the 2D interpolation technique, which can be done by this command in MATLAB between the points. Then we can ask the question that what would happen in each iteration over the mesh grid point. For the each mesh point or coordinates XY on a die, an iterative algorithm should be performed to obtain the variation in channel spacing and resonance wavelength shift of each ring. In this algorithm, we change the width of the ring according to FPPs to have the minimum channel spacing shift due to variations. For calculating the shift in the resonance wavelengths in each mesh point grid, which can be initiated and which can be showed by X and Y coordinates, we have to take into the account the variations due to thickness and the width and the slopes of the change in the resonance wavelength according to the with respect to the width of the input waveguide, ring, and thickness. These data, the values of the slopes, which can be here, can be read from these plots, which has been taken from this paper. And these values for each X and Y can be read from the interpolated mesh grids based on the FPVs that we have initially. In this paper, in this figure that we can see here, we can see that the width of the ring and the width of the waveguide are the same. We call this case the conventional case. And in this paper, we can see that the slopes are for the case that the width are the difference. And we call it the unconventional case. So the algorithm flowchart could be shown as here. First, we have been provided with the .csv files of the variation. We read them, we plot them, and we interpolate between them for the selected die called meshing. Then we fed the meshing to a for loop or an iterative loop to calculate the channel spacing and the variation in the resonance for a given geometry and for given variation for each point of the mesh according to this formula that we can see here. Then the results would be fed into the function. We change the width of the ring and again calculate the optimum change in the channel spacing, and we report the width of the rings, ring 1 and ring 2, which could lead to the least variation in the channel spacing. Then we select the width of the ring with the minimum change in the CS. We do the loop for all of the XYs of the selected die and the mesh. And then at the end of the iteration through the mesh points, select a proper width, which can be obtained by the mean value of all of the points for ring 1 and ring 2 and place the device in the selected die. Before we jump into the simulation specifications, just let's introduce some simulation specifications. The initial width of the ring 1 and ring 2 and the IO waveguides has been set to 400 nanometer. The gap has been set to 100 nanometer. The mesh accuracy is 10 nanometer. The wavelength of the central wavelength or resonance wavelength of the first ring has been set to 1.55 micrometer, and the next wavelength can be obtained by just adding the channel spacing, the multiplicand of the channel spacing to the initial wavelength. Then we iterate through the distances between the rings from a low level value, which is 10 micrometer, and we go through the highest value, which is 700 micrometer distances between the rings on the selected die, and we will see the results. And then we iterate through the variations, and then we iterate through for different values of the channel spacings from 3 to 10 nanometer. The waveguide width variations are 4.9 nanometer. The SOI thickness variation is 1.5 nanometer, and the radius variation is 7.5 nanometer. This is the results for the channel spacing of 6 nanometer when we iterate through the distances from 10 to 700 micrometer. And we can see that for the conventional case where the width of the input waveguide and the rings are the same at 400 nanometer, we can see as we increase the width, the variation in channel spacing would increase linearly. The same thing happened with the case of unconventional case. And when we have chosen the optimized width for the ring 1 and ring 2, we can see that as we increase the distance between the rings on the selected under the fabrication process variations, the variation in the channel spacing is not that much as the previous cases. Then turning to the mean value of the optimized width for the selected die for the ring 1 and ring 2, we can see that as the distance between the rings kept low, the width of the rings are almost the same. But when we increases the width between the rings, here we can see that the width of the ring and the width of the ring 2, which has been reported by the optimizer value, are different from each other. And the simulated results has been done for the case of channel spacing equals to 6 nanometer. In this plot, we kept the distance the same, 200 micrometer, and then we iterate over the channel spacing, and we can see that as we change and we increase the channel spacing, the optimized width of the ring 1 and ring 2 would be the same. So we can see that the design that we have is more sensitive to the distance between the rings rather than the channel spacing that we want. And turning to simulation results and simulation time, we can see that as we increases the distance between the rings, the simulation time would increase significantly. Whereas we increase the channel spacing, the simulation time would again increases, but the increase is not that significant when we compare it with the case of changing the distance between the rings. And this is the conclusion where my colleague will take over.
So, conclusions based on the methodology we used and the simulation results we saw, we studied that the process variations affect the overall performance of the MRRs and observed that by using the Monte Carlo method, though it is time consuming, gives almost accurate results. As for the variation effects, we observed that as the channel spacing and the distance between the pair of MRRs increased, its execution time increases. Also, that having an optimized placement and design based on the variation maps is important to reduce the shift in the channel spacing. Based on the observations, we can conclude that the automated design is more sensitive to the distance between the rings when compared to the channel spacing. And by taking into consideration the modified geometry, the channel spacing shifts can be minimized. As additional material, we have included our variation maps for interpolated mesh. These maps shown are in terms of the thickness, width, and the radius variations. So in here, the blue areas are least affected due to the fabrication process, and the red ones are the most affected areas. The automated placement algorithm will avoid placing the devices in the affected areas and place them in the safe zones. For the contribution done for performing the project, Amin Shafi took the liberty to develop the MATLAB code in order to do the optimal design and placement of MRRs on the die with variations in distance between the microring resonators based on the thickness, radius, and width variations. And I performed the placement of MRRs with respect to the variation in the channel spacing between the microring resonators. All the references are included here that we have used. Thank you so much for watching our presentation.